Good morning everyone. Today I am start the chapter of the organic chemistry, that is the nitro compound. First is the introduction. Nitro compound are an important class of the organic compound which may be regarded as derived from hydrocarbon by the replacement of one or more hydrogen atom by the nitro groups. Nitroarenes group is directly attached to benzene ring, can be prepared rather easily and have been used as synthetic reagents since long. But nowadays, even nitroalkenes are being prepared and used on a large scale. Structure of the nitro group. Nitro group is quite often represented as containing a double bond between nitrogen and one oxygen and a coordinated additive bond between nitrogen and the other oxygen. But actually nitro group is stabilized by the resonance and is a hybrid of the two equivalent contributing structures. The resonance hybrid structure is confirmed by the fact that the bond length of the each nitrogen oxygen bond is 121 pm, which is intermediate between NO single bond length, that is the 136 pm, NO double bond length 115 pm. In case of the nitroarenes, resonance of the nitro group with the ring can also take place, giving rise to additional contributing structure of molecule. It will be interesting to note that the nitro group is isoelectronic with carboxylate anion. Nomenclature of the nitro compound. Nitro compound are named as by the writing the word nitro before the name of the parent compound. The number of the nitro group and their position are also stably indicated as illustrated below. For example, nitromethane CH3NO2. Classification of the nitroalkenes. Nitroalkenes are termed as primary, secondary or tertiary according as a nitro group is attached to a primary, secondary or tertiary carbon atom, that is the RCH2NO3, RRCHNO2, RRRCNO2. Preparation of the nitro compound. First is the preparation of the nitroalkenes. Nitroalkenes are usually prepared by following method. First is the vapor phase nitration of alkene. The reaction involves the substitution of a hydrogen atom of alkene by a nitro group. It is carried out in the vapor state by heating the alkane with nitric acid at about 700 K. Limitation of the process. During nitration of the higher alkenes, all possible isomeric nitro products are formed. Moreover, rupture of carbon-carbon bond also take place, leading to the formation of the nitroalkene containing lesser number of the carbon atoms. Due to the formation of complex mixture of the product, this method is not used for the laboratory preparation of nitroalkenes. However, the method is widely used for the commercial preparation of the nitroalkenes. Mechanism. The reaction is believed to involve the formation of free radical, but the mechanism is not well established. Second is the action of the silver nitrate on alkyl halide. This is the method generally employed for the laboratory preparation of nitroalkenes. When heated with silver nitrate, alkyl halide undergo nucleophilic substitution to form nitroalkenes along with small quantity of alkyl nitrate. This is because NO2 negative is an ambident nucleophile. However, the mixture of the alkyl nitrates and the nitroalkene can be separated by fractional distillation. Oxidation of the amine. When an amine in which the amino group is attached to a tertiary carbon atom is oxidized with potassium permanganate, a tertiary nitroalkane is obtained. Preparation of the nitroarenes. Nitroarene are almost invariably prepared by direct nitration of arene. The nitrating agent generally used as first is the concentrated or fuming nitric acid. Second is the mixture of the concentrated or fuming nitric acid and concentrated sulfuric acid. This mixture is most commonly used as nitrating agent. Third is the mixture of the concentrated nitric acid and the acetate anhydride or boron trifluoride. Fourth is the acetyl nitrate obtained by mixing nitrogen pentoxide and the acetic anhydride. Fifth is the nitrogen peroxide in the presence of anhydrous aluminium chloride. Choice of the nitrating agent. The choice of the nitrating agent to be used for the nitration of a given compound depend upon the following two factors. First is the nature of the compound to be nitrated. Second is the number of the nitro group to be introduced. In the nitration of the aromatic compound containing electron releasing or activating groups such as the NH2, OH and CH3, the reaction takes place readily at room temperature by employing concentration HNO3. In some cases, even dilation HNO3 can be used. For example, phenol plus dilution of HNO3 is equal to phenol OH NO2 plus phenol OH NO2 plus H2O. For nitrating compound containing electron attracting or deactivating groups such as the COOH, or when it is desired to introduce more than one nitro group, a stably strong nitrating mixture has to be employed and the reaction is carried out at high temperature. Nitrobenzene and M-dinitrobenzene for intense can be obtained from benzene under the conditions shown as below. Mechanism of the nitration. Nitration of aromatic compound, like other aromatic substitution reaction, is electrophilic in nature and involves a nitronium ion NO2 positive as the attacking electrophile. The mechanism may be summed up as follows by considering the nitration of benzene with nitric acid sulfuric acid mixture. First is the generation of electrophile. Second is the formation of carbocation ion. Third is the proton transfer from the carbocation to yield the final product. Evidence in favor of the above mechanism. It has been shown above the aromatic nitration involves a stepwise mechanism. The nitronium ion, which acts as the electrophilic reagent, is generated in a preliminary steps and bring about the further reaction in two steps. The first step is a slow rate determining step involving the addition of nitronium ion to the aromatic ring to form a carbocation intermediate. The second step, which is relatively fast, involves the elimination of a proton from the intermediate ion by the heterolytic cleavage of CH bond. First is the C6H6 plus NO2 is equal to C6H5 positive H NO2 slow. Second is the C6H positive 5 H NO2 plus HSO4 negative is equal to C6H5 NO2 plus H2SO4 fast. The mechanism has been fully supported by the isotope tracer technique as explained below. If an aromatic compound labeled with deuterium is subjected to nitration, it is found that the rate of the substitution of the deuterium is the same as that of the ordinary hydrogen or plutonium. In other words, no isotope effect is observed, since a carbon deuterium bond is broken more slowly than a carbon protium bond. The absence of the isotope effect in aromatic nitration can be justified only if the rate determining step of the reaction does not involve any cleavage of the carbon hydrogen bond. This means that the final step involving the abstraction of the proton through the cleavage of the carbon hydrogen bond cannot be the rate determining step. Therefore, the step leading to the formation of the carbocation must be the rate determining step, as it does not involve any cleavage of the carbon hydrogen bond. Once formed, the carbocation loses the proton relatively fast to form the final product. The absence of the isotope effect also rules out the possibility of a single step mechanism for nitration. This is because single step substitution cannot take place without the cleavage of the carbon hydrogen bond. As such, it must exhibit isotope effect, but this is not in actual practice. Hence, aromatic nitration is a stepwise process in which the formation of carbocation is the rate determining step. Comparison of the nitration of arenes and the nitration of the alkenes. It may be noted that the nitration of the arenes take place at relatively low temperature, whereas the nitration of the alkene require a very high temperature. This may be due to the fact that the nitrogen of the arene involves the initial formation of the electrophilic reagent, while the nitration of the alkene is supposed to involve the initial formation of the free radical. The formation of the free radical takes place through homolysis and requires stronger condition than the formation of electrophile, which take place through heterolysis. As such, nitration of the arene take place more easily than the nitration of alkene. Nitroalkene cannot be prepared by the action of the silver nitrate on aryl halides because of a very slow reactivity of aryl halides towards nucleophilic reagent. Physical property of the nitro compound. First is the physical state. Nitroalkenes are colorless, oily liquid when pure. They have pleasant smells and are springly soluble in water. With the exception of a few compounds including nitrobenzene, which are yellow, oily liquid, all other aromatic nitro compounds are yellow, crystalline, solid. Nitrobenzene has an odor of bitter almonds and is known as oil of the midbane. Second is the solubility and density. All nitro compounds are heavier than water. Nitroalkenes are springly soluble in water, while aromatic nitro compounds are insoluble in it. They are, however, readily soluble in organic solvents such as alcohol and ether. Third is the stability. When heated strongly, polynitro compound decompose with exclusive violence. Fourth is the boiling point. Due to the presence of the highly polar nitro group in the molecules, nitro compounds have stronger dipole-dipole interaction. Consequently, they possess high boiling points, much higher than the hydrocarbons of the comparable molecular masses. However, the most of the nitro compounds are volatile in steam. The melting and the boiling point of the nitro compound gradually increase with the number of the nitro groups as illustrated ahead. Chemical reaction of the nitroalkenes. The important chemical reaction of the nitroalkenes as follow. First is the acidic nature. Teutomerism. Nitroalkene containing alpha hydrogen atom exhibit acidic behavior and form salt in the presence of strong alkalis. For example, RCH2NO2 plus NaOH is equal to bracket RCHNO2 bracket close negative Na positive plus HO2. The acidity can be attributed to the fact that first is the nitro group has a stronger electron withdrawing inductive effect. Second is that the anion formed after the removal of the proton from the nitroalkene get resonance stabilized due to the ability of the nitro group to accommodate negative charge. It is interesting to note that the salt formed by the nitroalkene is acidic at low temperature. The oily group of the nitroalkene do not separate immediately, but we get another form of the nitroalkene known as acynitro form, which slowly changes into the nitro form. This is due to the fact that the primary and secondary nitroalkane exhibit teutomerism, the teutomerism form being nitro form and acynitro form. Nitro form are CH2 N positive, double bond O, single bond O negative. Reversible reaction are CH double bond N positive, OH O negative, that is the SC nitro form. The teutomerism equilibrium between the two forms lies almost completely towards the nitro form because it is stabilized by the resonance of the nitro group. SC nitro form is relatively stronger acid than the nitro form. An important feature of the SC nitro form is that it can act both as electrophile and a nucleophile. Unlike primary and secondary nitroalkene and tertiary nitroalkene do not have any alpha hydrogen atom, as such they exhibit neither acidic character nor teutomerism. Second is the reduction of the nitroalkene. Reduction of the nitro compound is one of their most important reactions. The reduction of the nitro group takes place in stages as shown as below. First is the nitro compound RNO2 is equal to RNO nitroso compound is equal to substitutes hydroxyl enzyme RNHOH is equal to RNH2, that is the primary amine. Second is the reduction in acidic medium. When reduced in acidic solution nitroalkenes from primary amines RNO2 nitroalkene plus 6H is equal to, in the presence of FeHCl, RNH2, that is the primary amine, plus 2H2O. Third is the catalytic reduction or the reduction with LiAlH4. Reduction with LiAlH4 or H2 in the presence of the nickel, palladium or platinum catalyst also yield the same product RNO2 in the presence of LiAlH2 or H2 or PT is equal the product of RNH2 plus H2. Third is the reduction in the neutral medium. If the reduction is carried out in neutral solution, the hydroxide derivatives is obtained. Nitroalkene RNO2 plus 4H in the presence of zinc NH4Cl is equal to the product of the RNHOH plus H2. The hydroxamine are readily oxidized to corresponding nitroso compound on warming with the Tollens reagent with gets reduced to metallic silver. This reaction is used as test for nitro compound under the name Baker's Millikan test. Hydrolysis. When boiled with the concentration HCl or H2SO4, primary nitroalkene undergo hydrolysis to form carboxylic acid and the corresponding salt of the hydroxam. For example, RCH2NO2 plus H2O plus HCl heat RCOOH plus NH2OH dot HCl. Secondary nitroalkene are hydrolyzed to ketones and nitrous oxide by boiling with concentration HCl. 2R2CHNO2 boiling HCl 2R double bond CO single bond R plus N2O plus H2O. Tertiary nitroalkene are not hydrolyzed by the acid. Fourth is the NEF reaction. When sodium salt of the primary and secondary nitroalkene are hydrolyzed by the boiling with dilute sulfuric acid, aldehyde and ketone respectively are aptone. The reaction produced through the ACI nitro form of the nitroalkene. For example, 2 R single bond CH double bond N positive single bond O negative Na positive single bond O negative plus 2H2SO4 is equal to 2R single bond C single bond H double bond O plus 2NaHSO4 plus N2O plus H2, that is the aldehyde. Fifth is the action with nitric acid. Primary, secondary and tertiary nitroalkene exhibit different behavior towards nitric acid. First is the primary nitroalkene react with nitrous oxide to form nitrorolic acid which dissolve in NaOH plus to produce a red solution. Second is the secondary nitroalkene react with the nitrous acid to form a pseudonitrols which have blue color but do not dissolve in NaOH. Third is the tertiary nitroalkene and nitroarenes do not react with nitrous acid since they do not contain any alpha hydrogen atom. The above reaction can be used by distinguishing between primary, secondary and tertiary nitro compound. 6 is the halogenations. When treated with the halogen is slightly alkene solution, primary and secondary nitroalkene undergo halogenation at alpha position. For example, nitroethane CH3 single bond CH2 single bond NO2 in the presence of Cl2 NOH product, that is the CH3 single bond CHCl single bond NO2 in the presence of Cl NOH product is the CH3 single bond CCl2 single bond NO2, that is the 1,1-dichloronitroethane. Nitromethane on chlorination in alkene medium gives the trichlorination methane CCl3NO2, also known as chloropyrene. Tertiary nitroalkene do not undergo halogenation because do not have alpha hydrogen. Second is the condensation with aldehyde. Due to the presence of active alpha hydrogen atom in term, primary and secondary nitroalkene undergo aldol type condensation with the aldehyde in the presence of a base to form nitro alcohols. For example, CH3 single bond C single bond H double bond O plus CH2 single bond CH3 single bond NO2 is equal to the product is the CH3 single bond CH single bond OH single bond CH single bond CH3 single bond NO2, that is the 3-nitro-2-butanol. Manich reaction. This is the condensation reaction between involves formaldehyde, ammonia or a primary or secondary amines and a compound having at least one active hydrogen such as primary and secondary nitroalkene. For example, secondary nitroalkene R2CHNO2 plus HCHO plus NH4Cl product is the R2C single bond NO2 single bond CH2 NH2 HCl plus H2, that is the nitroamine hydrochloride. The reaction can be used for preparing nitroamines, diamines, etc. Chemical reaction of the nitroarenes. Nitroarenes are chemically rather inert compound. The nitro compound is firmly attached to the nucleus and cannot be replaced by the other atom or groups under ordinary conditions. Their important reaction are as follows. First is the acidic nature. Unlike primary and secondary nitroalkene, nitroarenes do not have any alpha hydrogen atom. As such, they do not exhibit acidic character or tautomerism. However, nitro compound having two or more nitro groups attached to a benzene ring are somewhat acidic in the nature due to the strong electron withdrawing effect of the nitro compound on the benzene ring. Second is the reduction. The most significant reaction of the nitro compound. As such, they do not exhibit acidic character or tautomerism. However, nitro compounds having two or more nitro groups attached to the benzene ring are somewhat acidic in nature due to the strong electron withdrawing effect of the nitro group on the benzene ring. Second is the reduction. The most significant reaction of the nitro compound in their reduction under different conditions to give different product. As already stated, the reaction take place in stages and the nature of the final product depend mainly on the pH of the reaction mixture. We will illustrate the reduction of the nitro under different conditions with the help of the nitrobenzene. First is the reduction in acidic medium. On reduction in acidic medium with an active metal with an active metal and acid such as zinc and HCl or tin and HCl. Nitrobenzene yields amylin. Nitrobenzene single bond NO2 in the presence of ZnHCl or SnHCl. That is, the product is the aniline plus single bond NH2 plus 2H2. Mechanism. The mechanism proposed for the reaction involves a number of steps in which the addition of electrons take place, and nitrobenzene free radical anion and the nitrosobenzene free radical anion are formed as intermediate. The mechanism may be summed up as follows: C6H5 single bond N positive double bond O single bond O negative in the presence of negative electrons. C6H5 single bond N positive single bond O negative single bond O negative in the presence of H positive. C6H5 single bond N positive single bond OH single bond O negative, that is the electron negative. C6H5 single bond electron plus 2 electron single bond OH, that is giving single bond O, that is single bond O give present N say electron negative in the presence of OH. That is, the product is the nitrobenzene C6H5 single bond N double bond O in the presence of electron free radical anion. C6H5 single bond N single bond O negative plus, in the presence of H positive. C6H5 single bond N single bond OH electron negative. C6H5 single bond N single bond OH in the presence of H electron. Hydroxylamine C6H5 NHOH in the presence of H positive. C6H5 single bond NH single bond OH 2 electron minus H2O. C6H5 single bond NH in the presence of electron negative. C6H5 NH in the presence of H. C6H5 NH2 aniline. Second is the catalytic reduction. Reduction of the nitrobenzene with the H2O in the presence of Ni and Pt catalyst also leads to the formation of aniline. Third is the reduction in neutral medium. When reduced in a neutral medium with the zinc dust and the ammonium chloride solution, the reaction stops at the hydroxylamine stops. Fourth is the reduction in the alkaline medium. On reduction in alkaline medium, nitrobenzene yields a different product depending upon the nature of the reducing agent employed. Phenol single bond NO2, that giving different product in the presence of ZnNaOH that produce hydroxybenzene, or in the presence of Na3ASO3 or NaOH that produce the azoxybenzene. These products are actually formed by the further reaction between the primary reduction products nitrosobenzene and phenyl hydroxyamine as shown below. Azoxybenzene is formed by the condensation of nitrobenzene and phenyl hydroxyamine as given as below. This is sufficient evidence to show that the azobenzene is be formed through the intermediate formation of azoxybenzene with its further reduction. Hydroxybenzene is similarly formed by the further reduction of the azobenzene. Fifth is the reduction with the LiAlH4. Reduction of the nitrobenzene with the LiAlH4 also yield azobenzene. Fifth is the electrolytic reduction. When reduced electrolytically in weakly acidic medium, nitrobenzene gives aniline, but on electrolytic reduction in strongly acidic solution, nitrobenzene yields p-amino phenol due to the rearrangement of phenyl hydroxyamine first formed. The electrolytic reduction in alkaline medium yields azoxybenzene, azobenzene, and hydrolobenzene. Seventh is the selective reduction. In case of the compound containing more than one nitro group, it is possible to carry out the selective reduction of one or group by employing a mild reducing agent such as ammonium hydrosulfide or sodium polysulfide. For example, M-dinitrobenzene plus 3NH4SH that gives the product M-nitroalene plus 3S plus 2H2O plus 3NS3. This reduction is known as Janine reduction. Third is the electrophilic substitution. Nitro groups being an electron withdrawing groups has a strongly deactivating effect on the electrophilic substitution reaction of the benzene nucleus. However, under strong condition, nitro compounds may undergo electrophilic substitution in meta position with respect to the nitro group. It may be noted that the nitrobenzene does not undergo Friedel-Crafts reaction. Fourth is the nucleophilic substitution. The nitro compound has no doubt a deactivating influence on electrophilic substitution in benzene nucleus due to its electron withdrawing nature, but this very electron withdrawing influence of the nitro group make the benzene nucleus liable to be attacked by the nucleophilic reagent. Thus, unlike benzene, nitrobenzene only heating with sodium hydroxide gives small amounts of the ortho and para nitrophenol. Mechanism. The mechanism of the reaction may be outlined as follows by considering the formation of p nitrophenol that produce the product benzene single bond OH, single bond N positive, single bond OS, O negative, double bond O plus H negative, yani hydride ion. Fifth is the replacement of the nitro group. In case of the polynitro compound, one of the nitro group itself can be replaced by the neutrophilic groups. For example, phenol single bond NO2, single bond NO2, that gives the reaction product in the presence of KH2 phenol OH single bond NO2 plus KNO2 p nitrophenol. In the presence of p dinitrobenzene gives the product in the presence of C2H2O and a p nitrophenitol. In the presence of 2NH3 that gives the product p nitroaniline.